I'm using this now. Hi friends, so today the topic of our discussion will be equilibrium. We'll be discussing both chemical and ionic equilibrium. So let us just start with the definition of equilibrium. Whatever you have studied from the books, that is all right, but what generally does equilibrium mean? It is basically just a balance between any two sets of things. It can be physical or chemical. Like here I have a pen. This pen is in equilibrium with the table. Even if I am moving it, it again goes back to the equilibrium. Its equilibrium position. If I change the position, it again goes back to its equilibrium position. It remains stable. So what equilibrium basically means is to be in a balanced mode. Okay? So in chemistry, however, we have equilibrium in reactions. So let us see some examples of a chemical equilibrium with the very own famous reaction, which is from the Haber's process, which is used for the manufacture of ammonia. The reaction is, so we are talking about equilibrium. So the reaction which we are talking about is when nitrogen and hydrogen combine to give you ammonia. Alright, here this equation is not balanced obviously, so we need to balance it. Since we have 1 mole of nitrogen which has 2 atoms of nitrogen, so here we'll have 2 moles of ammonia, and similarly we'll have 3 moles of hydrogen. So the symbol that we use here is a symbol of reversibility. So this symbol denotes reversibility. All the equations which are in equilibrium are reversible too, which means that the reaction can go forward as well as backward. Hence the sign, hence the half arrows. We can also write full arrows, that is not an issue. We can give them both ways, either this or this, which shows reversibility of an equation. Alright, so when a reaction is in equilibrium, we define a K. Alright, this K will be equal to the concentration of the products to the power of the coefficients. Here I am talking about the Haber's process, so let me just check for the equation that we already have. So here for K will be concentration of the product, which is ammonia, raised to the power of the coefficient, which is 2 for ammonia, divided by concentration of the reactants, which is nitrogen, to the power of its coefficient, which is 1, into the other, which is hydrogen, raised to the power of 3. So this is the formula. In general, we can say the formula will be K is equals to concentration of products to the power of their coefficients upon concentration of reactants to the power of their own coefficients. Alright, let's see what kind of problems we have with respect to solving for equilibrium constant. So if I am given that I have, let's talk about the same Haber's process, and if I am given that the amount of nitrogen is 28 grams, alright, and the amount of hydrogen given to me is 6 grams, alright, and if they are kept in a vessel at the temperature of 400 degrees Celsius, then what will be our value of K? So we have the amount of nitrogen to be 28 grams, the amount of hydrogen to be 6 grams, temperature is 400 degrees Celsius, the volume of the vessel is 1 liter, and one extra information that we are given is that at equilibrium the mixture contains NH3, that is ammonia, equal to 27.54 grams. This value is at the rate equilibrium. So how do we solve this problem? How do we find the equilibrium constant? Let's see. Alright. So I have this equation 2, and I have this equation N2 plus 3H2 gives 2NH3, correct? So let's see how many moles do we have for nitrogen here. So for nitrogen, the mass, molar mass for nitrogen comes out to be 28 grams, right? And we have the mass as 28 grams. So the moles for nitrogen will be 1. For hydrogen, the molar mass is 2 grams, whereas initially our hydrogen amount is 6 grams. Hence the moles that come out for a hydrogen will be 3 moles, correct? And initially at t equals to 0, ammonia is 0, correct? Now when time passes at equilibrium, so the amount of nitrogen that reduces is x times, right? But as we can see that for 1 mole of nitrogen, 3 moles of hydrogen are reacted. Hence the amount of hydrogen that will react will be 3 times x, correct? And the amount of ammonia that is formed by 1 mole of nitrogen is twice. So the ammonia that will be formed will be 2 times x. So this will be our products at the equilibrium. Initially we had 1 mole of nitrogen and 3 moles of hydrogen and 0 moles of ammonia, whereas at equilibrium, when x moles is reduced from nitrogen, 3x will be reduced from hydrogen and 2x will be formed at ammonia, correct? So now what we are given is that at equilibrium we have 27.54 grams of ammonia. So what we know is that mass of ammonia is 17 grams. So how many moles will it be? So that will be 27.54 upon 17, correct? Which comes out to be approximately 1.6 moles. And this 1.6 moles are at equilibrium, which is the same number as this. Hence we can say, what we can find from here is x. What we can find is x is 0.8. Once we know that x is 0.8, we can easily find out Kc. So we know that x is 0.8. So at equilibrium time, what we get for N2 is 1 minus 0.8, that is approximately 0.2. And here for 3 minus 3x, that is 3 minus 2.4 becomes 0.6, and here we get 1.6, correct? So now we can calculate K easily by substituting the concentration terms. Now we have the volume also. The volume is 1 liter. So these are just the moles, correct? So we need to divide the whole mole with the volumes. So 1.6 by 1, that is 1.6 moles per liter for ammonia in the to the power of its coefficient, which is 2, divided by 0.2 for ammonia, 0.2 moles per liter for ammonia to the power of 1, and 0.6 moles per liter of hydrogen to the power of 3, correct? So this will give me the solution to this problem. We can solve this further and we can calculate the answer for K. Any issues? So we can move further with this. So the second thing which is important in understanding the chemical equilibrium is talking about the Le Chatelier principle. So obviously you must have, it is very important for the exam point of view, and you must have studied a lot about this in exam, but you must have studied all the book definitions. Let us understand it in very simple words. What does Le-Chatelier principle actually mean? So basic principle, the mantra for Le-Chatelier principle is that equilibrium resists the change. That's it, the one line. Equilibrium resists the change. How? Let's understand. So basically the factors involved in changing the equilibrium are basically pressure, temperature, inert gases, there is concentration, there is volume. There are many factors involved. We'll talk about only 2 or 3 factors. Alright, so let's see how pressure, how some factors bring the change and how the equilibrium resists the change. Alright, so here again we are taking the same example of our Haber's process, that is the manufacture of ammonia. We have N2 plus 3H2 gives 2NH3. Correct? Now, what we know about these reactions, let us understand all the factors that we already know about these reactions. Here, this reaction, while going to the forward direction, is exothermic in nature. That means it evolves heat. Delta H is negative when in forward direction. Obviously, in the backward direction, that will be endothermic. So, when ammonia breaks down into hydrogen and nitrogen, it will be a endothermic reaction. Secondly, what we know about this reaction is that on the reactant side we have total 4 moles of reactants, whereas on the product side we have total 2 moles of product. Alright, so this all information we have. So let's see how the changing pressure or changing temperature will bring the change in the reaction through Le-Chatelier's principle, which says equilibrium resists the change. So here let's talk about pressure first. So what if I increase the pressure in a system? What happens? So when I increase the pressure, now what will equilibrium do? It will resist the change. It will try to decrease the pressure. So to decrease the pressure, what will it will just take the reaction towards the side where the number of moles are less. Why? Because lower moles means lower pressure. Hence the reaction will start moving in the forward direction as I increase the pressure. So when I increase the pressure, so here in the reactant side we have 4 moles, whereas on the product side we have 2 moles. So to resist the change, to resist the pressure increase, the equilibrium will try to shift towards the forward direction where it will be able to decrease this pressure, hence resist the change. Alright, so if I decrease the pressure, on the contrary, this will take it to forward direction. On the contrary, again, if I talk about decreasing the pressure, if I decrease the pressure, so when I decrease the pressure, again the whole system will try to increase the pressure of the system, right? Now to increase the pressure of the system, it will have to move in the direction where the number of moles are greater, and the number of moles of greater are on the left side, which is the reactant side. Hence the reaction will start moving more towards the backward direction and it will look more like this. It's a backward reaction. Backward is happening more than the forward. Correct? Now, second thing that we can talk about is temperature. Now, this temperature is also related to the reaction's heat, whether the heat is been given out or the heat has been absorbed by the reaction. Right? So, when the temperature, what happens if I increase the temperature? Let us understand that. So, when in the reaction vessel, if the temperature is increased, so what the system will want is to reduce the temperature. Now, as we can see, while going to the forward side, what is happening is it is an exothermic reaction. That means the temperature that the heat is being evolved. So heat is being evolved means temperature is being increased. But while if we see the backward reaction, the heat is going to be absorbed. That is an endothermic reaction, which will reduce the temperature. So if I increase the temperature, the system will want to reduce the temperature, and to reduce the temperature the reaction will go in the backward direction, which will be towards the reactant side. Hence for exothermic case the reaction will go backward. Easy, right? Similarly, the temperature is decreased, and we are talking about a exothermic reaction here. Since the temperature is decreased, so to increase the temperature it will have to evolve more heat, and to evolve more heat it will go into the forward reaction side. Hence it will take a forward case. Alright, so moving on, if you have doubts you can ask on the chat. Let's move on to the other important topics related to ionic equilibrium, which are very important in the competitive exams. So let's check some questions related to that too. So next we can talk about, in ionic equilibrium, very important concept is Ostwald Law of Dilution. So in ionic equilibrium, let's check it out with an example. We have CH3COOH. So what we know is that weak acids basically generally do not break down completely, right? Because of their weak nature. Hence they have a degree of dissociation involved with them. So let us assume that initially the concentration of CH3COOH was C. With time we can say that some of its parts broke down. Let's say the degree of dissociation is alpha. Alright, degree of dissociation is alpha. So the part which broke down from CH3COOH will be C alpha. Hence the reactant will decrease by this term, which is degree of dissociation into the initial concentration, which gives us the concentration which broke down for CH3COOH. And because the coefficients are 1 overall, hence the same amount will be formed in the case of CH3CO minus. The amount which is broken down from CH3COOH will be visible in the ionic form, which is C alpha and H plus, which will be also C alpha. Correct? So now to calculate this alpha, we can to calculate the K, basically what we can do is we can again go back to the same formula that we have been using, which gives us C alpha to the power of 1, C alpha to the power of 1 upon C minus C alpha to the power of 1. Here from bottom we can take the C denominator, we can take the C common, and we can cut it with C on the numerator, which hence this becomes C square alpha square C 1 minus alpha C alpha square upon 1 minus alpha. Now this is a general equation for K, right? This is a general equation for K, and here if this alpha is very small, then it can also be neglected. When this is neglected, we can directly calculate the value of alpha if the K is given, and if K is not given, alpha is given, we can calculate the K, and if K and alpha is given, we can calculate the value of C. But it is only possible when the alpha is very small as compared to 1. So it has to be around below 10%, then only it is possible. Otherwise we don't generally neglect it, and we have to involve it and solve the quadratic equation, which obviously you have learned in the mathematics, so you can do it, you can take it proceeded further. Here we'll talk about some variations with respect to these kind of problems. So now I have calculated, let's assume that I am given K. So now we know that H plus is C alpha. From here, this value we can also calculate what? Alpha from here, and then we can calculate C alpha, which is the H plus. So H plus ion concentration can also be calculated from these kind of problems, which will be just C alpha, right? So here I am just assuming that the alpha is negligible, that is alpha is very less than 1. So in such cases, when alpha is very less than 1, so k is equals to c alpha square, and alpha becomes root of k by c, correct? Hence when I want to calculate h plus, it can be given as c alpha, which will come out as c times root of k by c, which is root of kc, which is h plus. From here, once I know h plus, I can calculate pH of any kind of solution. Alright, so to find out the pH, we have the simple formula of pH is equals to minus log of concentration of H plus. Hence, from here we can calculate H plus and pH too. Let's take a problem involving pH. A very simple problem. So, if I am given a solution, HCl solution, whose concentration is 10 raised to power minus 8 molar, and I am asked to calculate the pH of the solution, then how do I calculate the pH of the solution? Alright, let's see. The pH is what we have to find. So, obviously you will be thinking, what's so difficult about it? We know pH is equals to minus log of H plus. Here HCl obviously will dissociate completely, right? And 10 to the power minus 8 molar of H plus will be our concentration of hydrogen ion. So what we'll do is directly put the 10 raised to power minus 8 here and solve it and find it 8. But for HCl solution, can we have 8 as our pH? Because for 8 is for a basic solution, and for acidic solution it always remains less than 7. So obviously this is the wrong approach. What we have to understand here is HCl in the concentration of 10 to the power minus 8 molar is very low amount of H plus concentration. Hence we also have to consider the concentration of H plus coming from HCl and water. What we know is that water produces 10 raised to the power minus 7 molar H plus, and from HCl we have 10 raised to the power minus 8 molar of H plus. So now what we need to do is add these two hydrogen ion concentrations, find the answer, and then finally calculate their pH. So what we do is 10 to the power minus 8 plus 10 to the power minus 7, which is approximately equal to 1.1 into 10 to the power minus 7. Now with this we can actually solve for pH, which will be minus log of H plus. Hence this will give us minus log of 1.1 into 10 to the power minus 7, which will be 7 minus log of 1.1. Hence the pH will come out to be approximately 6.96, which is an approximate value which can be taken out by a log table. This is a very important process that you have to remember. For a very dilute solution, for 10 to the power minus 8, 10 to the power minus 9m solutions for HCl, you have to consider the concentration of hydrogen ions coming from the water. Otherwise your problem can go wrong. The solution will be not right. Alright. Further, let's also discuss about buffer solutions. So what are buffer solutions? Let's first talk about that. So there are times when we have a weak acid such like a CS3COH, acetic acid, alright, and its salt like CS3COONa. When a weak acid and a its own salt, they come together in one solution. These kind of solutions, a weak base with its salt, they come in one solution. These kind of solutions are known as buffer solutions. Why they are known as buffer solution is because of a basic property of a buffer, which is it resists a pH change. It will not let the pH value being changed. Also, we have buffer in our blood. It is a carbonate and a bicarbonate salt buffer, and because of that only we are able to survive in this hostile environment around us. Otherwise we would have died. So all these pathogens and all the bacteria that come to our bloods, they actually die because they did not let the buffer on the blood does not let the pH change. Hence it remains as a constant, and it acts as a hostile environment for all the pathogens and bacteria coming in our body, right? So let's see, we know how buffer is formed. Let's discuss about a problem here. So here is one problem we have. If 50 ml of 0.2 m KOH is added to 40 ml of 0.0 m HCOOH, the pH of the resulting solution is. So what we are given here is KOH, which is 50 ml volume and 0.2 m concentration. Now this is given with formic acid HCOOH, which is 0.5 m concentration in 40 ml solution, alright, and the K of the HCOOH, that is the formic acid, is 1.8 into 10 raised to power minus 4. So these kind of questions are also important from the exam point of view. Let us understand how to solve them. So here we have two things. One is KOH, which is a base, a strong base, which is 0.2 m 50 ml. So how many millimoles? We have 10 millimoles, correct? Secondly, we have in the solution formic acid, which is HCOOH, which is a weak acid. This is 0.5 m in 40 ml, that is 20 millimoles. Now what will happen now is this weak acid and this strong base are in the same vessel, and what we know about this is that a basic base and the acid reacts to give us a salt and water. That is a simple neutralization reaction. So here also we'll find out that HCOOH reacts with KOH to give what? To give you HCOOK plus H2O. So we have 20 millimoles of HCOOH, whereas 10 millimoles of KOH. Initially these are 0. Finally what will happen is the KOH, being a strong base, will completely dissociate, correct, and react with HCOOH. Hence after some time in equilibrium, KOH will be 0, and the complete 10 millimoles of KOH will react with HCOH to give HCOK. Hence HCOH will be left as 10 and HCOK will be 10 too, and the amount of H2O is also 10. And this whole thing is going on in a 90 ml of solution. 50 ml of KOH and 40 ml of HCOH, total of 90 ml of solution, right? So now what we are left with is HCOH and HCOK. So what we can say is here HCOH plus HCOOK, what they form? They form a buffer solution, correct? Now to calculate the pH of a buffer solution, we have to remember two equations. So the two equations which are important for understanding the calculations of the buffer solution, they are known as Henderson-Hasselbalch equations. So these are the two people who came out with these equations, and hence this names belong, hence the name. So what are these equations? These are two different equations for acidic buffers as well as basic buffers. For acidic buffers, we say that pH is equals to pKa plus log of concentration of salt upon acid. Alright, whereas this is for acid buffer. Whereas if you want to calculate for basic buffer, since it's a base involved, we can't find the pH directly, we'll have to find the pOH. So the pOH will be equal to pKb plus log of concentration of salt by base. So this is for a basic buffer. Alright, so these are the two very important equations that we have to note down for solving and finding the pH and pOH of a buffer solution. Alright, so coming back to our problem. Now what we have here, look at this, what we have here is a buffer solution of acidic buffer solution of two things, formic acid and formic salt. We have 10 millimoles of each, correct? So using the first equation, we can find the pH as pKa plus log of concentration of salt. Now concentration of salt can be found out as moles of salt, which were 10 millimoles in 90 ml of solution, correct? And it will be divided by concentration of acid, which was again 10 millimoles per 90 ml of acid, which will come out to be 1. Now, so log of 1 is 0, hence pH for this equation will be equal to pKa. What we know is K is 1.8 into 10 to the power minus 4. So we can easily find out pKa from here. So pKa will come out to be 4 minus log of 1.8. Right? So obviously it will be lesser than 4. So this will be the answer, 3.75. Since log of 1.8 is approximately equal to 0.25, so the answer will be approximately 3.75. All right. Now, so this was about buffer solutions. Next, in line, let us talk about the equations related to the hydrolysis, salt hydrolysis. Now, this is a very important theory. Kindly understand this. What we have is, now we have weak acids, weak bases, right? Strong acids, strong bases. So the salts can be formed by any of the mixture of two. We can have strong acids and strong base react to form salts, we can have weak acids reacting with weak base to form salts. We can have weak acids reacting with strong bases to form salts, as well as strong acids reacting with weak bases to form salts. So we have strong acid, strong base, weak acid, strong base, strong acid, weak base, and a weak acid and a weak base. All these can react with each other to form salts. Now, generally, the salts which are formed by strong acid and strong base are completely broken down into their ions in the water. Right? Example is NaCl. So NaCl is a salt of sodium hydroxide and hydrochloric acid. Both are strong acid and a strong base. Hydrochloric acid is a strong acid, whereas sodium hydroxide is a strong base. So the salt formed is NaCl. Hence it gets completely ionized in the water. So this salt cannot be hydrolyzed. Why? It can't react with water because the strong acids and the strong base, when they will break down to form the salt, the conjugate acid and bases formed will be weak. Such conjugate acids and bases which are weak in nature cannot react with water, right? And hence they can't go back and form the salt, form the acid or the base from the salt. Hence these kind of salts do not hydrolyze. So we are left with these three. So examples, I will give you the examples for a weak acid and a strong base. So what happens if I react acetic acid with sodium hydroxide? What we get is CH3COO Na. So this is a salt of a weak acid and a strong base. For a salt of strong acid with a weak base, we have we can react HCl with ammonium hydroxide. So NH4OH plus HCl will give us NH4Cl. This is a salt of strong acid and a weak base. Whereas for a salt of weak acid and a weak base, we can directly react acetic acid with ammonium hydroxide and get CH3COO NH4. So this is a salt of weak acid and a weak base. So these three salts can be hydrolyzed very easily, whereas a salt of strong acid and strong base cannot be hydrolyzed at all. Alright, so let us see the equations which are important for the hydrolysis of these three kind of salts. We will talk about these weak acid and a strong base first. So as we can say, see that it's a weak acid and a strong base. So after hydrolysis, what will happen? The pH of the salt will be more than 7 because the base is stronger. So from the equation also we can see for a weak acid and a strong base, the pH after the hydrolysis equation comes out to be 7 plus half of pK plus log C. The K is the constant for weak acid. C is the concentration. If we talk about a strong acid with a weak base, the pH value will fall towards the acidic side. Why? Because we have a strong acid with a weak base. Hence you will see it will be lesser than 7. In the first case it was more than 7 because of a strong base. In this case it will be lesser than 7. 7 minus half of pKb. This time we are talking about the weak base. Hence we are talking about the constant for the base which is involved, because that is which is weak. The acid which is very strong will be hydrolyzed easily, correct? It will be completely, it will be in the solution, whereas weak base doesn't break completely. Hence we are talking about constant for the base plus log C, the concentration of the salt. Now talking about a weak acid and a weak base. Now in this case both will be hydrolyzed equally. So depending upon the, so both of the constants involved for weak acid and weak base will be visible in this equation, and also the pH, the acidity or the basicity will be depending on whatever salt will be hydrolyzed more, whatever the acid or whatever the base will be hydrolyzed more to give the more salt, more acid or base. So if the salt hydrolyzes to give more acid, then it will be lesser, the pH will be less than 7. If the salt hydrolyzes to give more base, it will be more than 7, right? So the whole pH comes out to be 7 plus half of pKa minus pKb. So these three equations are very important from the exam point of view, and generally the questions which are involved are being asked for the to calculate the value of pH only. Alright, now another thing that is important for understanding in equilibrium, ionic equilibrium, is solubility. So when I talk about a solubility of a substance, so it has many applications also. So the constant, the equilibrium constant for solubility will be Ksp, solubility or solubility product. What does solubility tells us about any substance is how much soluble or insoluble a substance is in a solution. So this is what a solubility product talks about, or we can directly say solubility also, right? As if I talk about, let's say we have AgI dissolved in a solution. So if AgI will be dissolved in a solution, it will break down into Ag plus and I minus, right? This is solid, whereas in the solution it will go to aqueous form. Let's say it is dissolved in water. So initially its solubility is 0, correct? But as soon as it is dissolved in water, there is some part which of Ag plus and there is some part of I minus which is dissolved in water. Let us denote it by S. Alright, hence what we can say is that Ksp is equals to S square. Alright, if the terms are involved, like let's say we have another salt like CH3COO whole twice Ca. Now this is dissolved in water. It gives 2CH3COO minus plus Ca2 plus. Alright, so now when this is dissolved, so what happens of solubility? This is 2S and this is S. So now when we calculate the Ksp, obviously again 2S square into S, which gives us 4S cube. This is the solubility product for CH3COO whole twice Cs. So we have to consider the coefficients and then calculate Ksp. This is very important concept. It also helps us in finding out the ionic comparison. It also gives us a comparison between solubility product and ionic product. It also helps us in finding out the precipitation, if it will occur or not. It will tell us whether the salt is soluble or insoluble inside a solution. All right. So there are many applications related to solubility product. Let us understand how we use it for our calculations through a question. So here I have another question for you. Now what I am given here is that the solubility product of AgI at 25 degrees Celsius is 1 into 10 to the power minus 16 mole square right, per liter square. The solubility of AgI is 10 to the power minus 4 normal. Here, since here molarity and normality will be exactly same for AgI. Alright, so Now solution of Ki at 25 degrees Celsius is approximately, now what we are asking for to find out is solubility of AgI. Alright, so we need to calculate that. Let's see how do we proceed. The question initially gives us that AgI, silver iodide at 25 degrees Celsius, has a solubility of 10 raised to power minus 16. Right? Now, after some time, it is dissolved with Ki at 25 degrees Celsius, and then we need to find the solubility of the whole solution. Alright, so if I have the solubility of AgI, can I individually calculate the solubility of Ag, solubility of product we have, right? What we are given is Ksp. So Ksp being equilibrium constant, solubility product constant, will not change throughout the system, throughout the whole process. So for AgI, that is 10 to the power minus 16. From this I can easily calculate solubilities of Ag and I, alright, which will be root of Ksp, because Ksp is equals to S square in this case 2. So Ksp is 10 to the power minus 16. That means S square is equals to 10 to the power minus 16, and S is root of 10 to the power minus 16, which will be 10 raised to the power minus 8. So what we know is that solubility of Ag plus is 10 to the power minus 8 in the solution, and solubility of I minus is also 10 to the power minus 8 in the solution. Right. Now further what we see is that we have added Ki, which is 10 to the power minus 4n, which can also be considered as 10 to the power minus 4m in this case. So here these are the solubilities of I minus and Ag plus. Correct. Now we have a I minus at 10 to the power minus 4 coming from Ki. So this is the concentration of I minus, solubility of I minus from 10 Ki. So what we'll have to do is, to find out the new solubility, we'll have to add I minus from old solution with the new solution. Since we can see that the difference in the power is a very huge difference, and this number as compared to this number is very small, we can neglect it. So now what we have here is the new I minus concentration, which is 10 raised to the power minus 4. Right. Now we know that the solubility product Ksp, which is constant, will not change, that is 10 to the power minus 16. Correct. So we can now calculate the solubility of Ag plus in this solution by giving the solubility of Ag plus with the I minus, which is Ag plus is S, and the I minus will have a new solubility, which will be 10 to the power minus 4. This whole thing will be equal to 10 to the power minus 16. So solubility of Ag plus will come out to be 10 to the power minus 16 upon 10 raised to the power minus 4, which will be 10 to the power minus 12. Here this will be our answer to the solution. Alright. In this theory, we have also understood one more concept, that is also called common ion effect. So as we saw just let us understand the concept of common ion effect. So what common ion effect here in the last question we saw was when we have AgI plus Ki, what we saw was that this I comes from both the equations. So this AgI breaks down to give Ag plus I minus, whereas this Ki breaks down to give K plus and I minus. So in our last case what we saw was that initially the solubility of Ag plus was 10 to the power minus 8, but due to the presence of more I minus, it reacted more with Ag plus and the solubility was decreased to 10 to the power minus 12. Why this happened was because of the presence of this common ion, which will react with both both ions will now react with Ag plus also, and hence this will give AgI more in the solution, as this is a very strong salt. So this will be completely dissociated as compared to AgI. Hence this will react more with Ag and the solubility of Ag will decrease. This concept of common ion is very much used in the salt analysis that you do in the in your laboratories in your 12th classes. So even in the group 2 reagents you see the use of HCl and H2S. Here also we have H plus coming from both the reagents, and it acts as a common ion, and here HCl is a strong acid, so it will dissociate completely in the solution, whereas H2S is not as strong, and hence it will be affected by this common ion H plus coming from HCl. Alright, so this was all with our theory from equilibrium. Any questions if you have? So we'll finish up now. Thank you very much. See you in the next classes. Bye bye.